Welcome to the Explainer. Today, we're doing something really cool. We're going to trace the fascinating journey of a single industrial command. We'll follow a signal right from the absolute lightest human touch on a button all the way to a crushing, massive mechanical force. Honestly, it's a surprisingly elegant process of translation, and I promise you, by the end of this, you're going to look at the automated world around you in a completely different way. Okay, let's dive right into our baseline objective. We need to command this massive metal piston to extend and retract safely from point A to a target, let's call it A'. Now the catch here is that we're using momentary push buttons. That means they only actually send a signal while your finger is physically pressing them down. And crucially, we have to absolutely guarantee that this system cannot possibly receive conflicting directional commands at the same time. I mean, if it tells the piston to push and pull simultaneously, yeah, things break. Badly.
So to actually move that heavy piston, we're going to need some serious industrial muscle. This usually means choosing between two different forms of fluid power. On one side, we've got hydraulic power. That's using thick, incompressible oil for extreme heavy lifting. And on the other side, we have pneumatic power, using pressurized gas or air for rapid, really high-speed cycling. Now here's what's actually really fascinating about this setup. We have these major physical differences, right? Hydraulics are slow, they can be messy, but they are insanely strong. Pneumatics are super fast, clean, but definitely weaker. Yet, despite all these extreme physical differences in force and speed, the underlying digital control logic, the brain we're about to build, it's going to remain exactly the same regardless of which muscle we actually choose.
But before we start flexing that industrial muscle, we have to build a safe nervous system. We really need to cleanly separate the electrical layers here. On the input side, human operators are interacting with a nice, safe, low-voltage 24-volt current. But the mechanical actuators, they require much heavier power to run. So the PLC, our programmable logic controller, sitting right in the middle, it acts as this absolute barrier between the two. This is so vital because it shields our delicate digital brain from the high-voltage electrical kickback that inevitably happens when massive machines power down.
So how exactly do we cross that gap? Well, we build a mechanical bridge using a 5-2-directional control valve. You can think of this valve as basically the ultimate translator between the digital world and the physical fluid world. On either end of it, there are these solenoids, which are essentially electromechanical triggers. They take that isolated, tiny digital whisper from our controller and they use it to unleash real physical movement.
Let's peek inside that metal block and witness what's called the spool shift. When one of those solenoids is energized with a current, it instantly creates a magnetic field. That invisible force then physically pulls an internal metal spool. And here's the crazy part. Just by moving that spool a tiny fraction of an inch, high-pressure fluid is instantly redirected, forcing the entire cylinder to move. We've successfully turned a super low-power electrical signal into immense mechanical action.
Okay, so we've got our mechanical bridge and our fluid muscle perfectly set up. But here's the terrifying question we still have to answer. What happens if an operator panics, or slips, or just makes a really dumb mistake and presses the extend and retract buttons at the exact same time? Because with massive industrial pressures at play here, a conflicting signal could literally tear the machinery apart.
To keep our machine from literally destroying itself, we rely on the system's brain. And this brain is programmed using a specialized visual software architecture known as ladder logic. It's called ladder logic because, well, it literally looks like a ladder. It's got these vertical power rails and horizontal rungs of code. But this code doesn't just passively read inputs. It isolates them, it quote-unquote remembers them, and most importantly, it uses mathematical interlocks to absolutely lock out those conflicting physical movements we were just talking about.
Now this digital brain has a very specific puzzle it has to solve. Because our push buttons are momentary, the system has to somehow remember the command to extend long after the operator's finger actually leaves the button. And while it's remembering that command, it has to simultaneously guarantee that the opposite command is strictly locked out. We pull this off through two really vital code patterns. Which brings us to our first brilliant solution, the latch. So when the operator presses the button, the signal reaches the output coil. Now here's where the magic happens. That output instantly closes its own parallel circuit, creating an OR gate. So now, when the operator releases the physical button, it doesn't even matter. The signal just bypasses it and flows right through the new path. The system has created a continuous loop. It has successfully remembered to keep pushing.
Right. But what about our panicking operator from earlier? To completely avert a mechanical catastrophe, we deploy a safety interlock. We take a normally closed contact of the retract button and place it directly in the path of the extend command. This creates an and not logic gate. By waving the opposite buttons directly into each other's paths like this, we mathematically sever the opposing control line. The cylinder physically cannot tear itself apart, even if someone is literally mashing both buttons.
Now, while we humans visualize this all as a nice ladder, the controller systematically reads these circuits as a high-speed logic matrix. It's processing this rapid-fire instruction set, loading the inputs, evaluating those or and not conditions, and then executing the safe outputs. It scans this list from top to bottom over and over again, thousands of times a second, with absolute, unyielding precision.
All right, let's watch this entire sequence rapidly come alive. Step 1, the human finger pushes the button, triggering that safe low-voltage input. Step 2, inside the digital brain, the PLC bypasses the interlock and latches the relay. Step 3, that relay sends a high-voltage signal right across the mechanical bridge to energize the solenoid. And finally, step 4, the spool shifts and high-pressure fluid aggressively drives that heavy piston forward to its target. Boom.
And the return journey, honestly, it's just as elegant. Almost instantly upon hitting that second button, the PLC software interlock automatically breaks the previous latch we just made. At the exact same time, it latches the second rung, energizes the opposing solenoid, shifts the spool back, and seamlessly routes the fluid to safely retract the piston. It is quite literally a perfectly choreographed dance of electricity, logic, and fluid dynamics.
When you take a step back and look at this complete architecture, you really start to see the true genius of industrial automation. The whole thing relies on deliberate decoupling. By explicitly isolating those fragile human inputs, deploying these highly intelligent software interlocks that completely outsmart human error, and shielding the digital brain from high-voltage brute force, we engineer systems that are incredibly safe, remarkably durable, and infinitely repeatable.
The crazy thing is, this exact same architecture scales up to run entire factories, power plants, and assembly lines all across the globe. So as we wrap up this explainer today, I want you to look around your own environment and just ask yourself, where else in your world are invisible digital brains hiding behind massive physical power? The logic we just explored together is everywhere, just waiting for you to notice it. Thanks for joining me on this deep dive, and keep asking how things work.